Thank you for coming to this presentation about my use of computation in a modern physics course. I want to start with two possible methods for teaching students a very important topic, the quantum mechanical harmonic oscillator. On the left, you see some page scans that are probably very familiar to many of us. Griffith's derivation of the energy levels and wave functions for the harmonic oscillator. This is a classic treatment that introduces the raising and lowering operators that are important later in second quantization and that demonstrates the power of using creative algebraic solutions to quantum mechanics problems. On the right, we see a computational activity in which the student is using sliders to adjust the energy level of the harmonic oscillator wave function to discover those energy levels and the shape and properties of the wave function. These presentations of the material have a lot in common. They both rely heavily on the Schrödinger equation. They both produce the same results of the energy levels in the wave function. And yet, the presentation on the left is very static. It's very focused on information transfer from the mind of the expert to the mind of the novice via a written medium. On the other hand, the presentation on the right is interactive. The student is getting an intuitive feel for the pattern in the energy levels and the behavior of the boundary conditions and the importance of having psi go to 0 as x approaches plus and minus infinity. I want to argue that both these approaches have their place. It's very important that we see mathematically where this derivation comes from, but I don't believe that the presentation as outlined in Griffiths should be the first exposure students have to this problem, because the method on the right provides them with a more hands-on, interactive, and memorable way of learning this material. After all, what do we as practicing physicists do more often on a day-to-day basis? Do we work with a code to solve a problem that we're interested in, or do we review a derivation that's been hashed over for the better part of a century? So now that you're thinking in terms of how we introduce difficult quantum concepts to our students, I want us to talk about the context of my junior level modern physics in a new department to me that is also new to the world of computational physics education. I want to talk about the resources that I made use of from Thephet and the PICUP collection, as well as a few new activities that I was able to develop as part of this course. Then I'll talk about how I use specifications-based grading to assess my students' learning in this course. And finally, I'll talk about interviews I conducted with my students after this course ended to get an idea of how computation helped them learn the difficult concepts of quantum mechanics. So in the summer of 2020, in the midst of the COVID-19 pandemic, I found myself unexpectedly searching for new employment. I'm very grateful to the physics community for supporting me during this past year. I'm grateful that I was able to continue my teaching, grow my research endeavors, and continue to serve through AAPT and PICUP, all without having to disrupt my family with a move. The list of names on the right represents everyone I could think of as I was preparing this presentation that I owe this past year to. I am sure I have left off many of you. Please know that you have my heartfelt thanks and commitment to helping this community continue to succeed. And to anyone who is watching this who is similarly experiencing a challenging time in their lives, I do encourage you to reach out to really just about anyone in the AAPT physics education community. People really are here to help and really do want to see you succeed. So in my first semester at the University of North Florida, I found myself having no time to prep as I taught modern physics for the first time in my career. I was encouraged to see that this department had recently started integrating computation. It's not really any secret that I love computation in any course that I can get it forced into. And I was also well positioned because this modern physics course in this program is the gateway to most of the upper level content. And so I decided to go all in with computational assignments. No traditional homework, just all computation-based assignments. So I was new to teaching modern physics. I certainly had never taught it with a computational emphasis. So I went to where I would recommend anybody start with integrating computation in their course, and that's going to the PICUP collection of exercise sets. PICUP hosts a broad collection of computational activities, numbering at, I believe, above 70 at this point in history, that you can adopt or adapt for your course. You can search the PICUP collection based on topic, based on what type of course it is, high school, introductory, beyond introductory. There are 2 tabs in the PICUP collection that you'll want to check out. There's the exercise sets, which are peer-reviewed. They come with all the bells and whistles, a complete set of features for everything you might possibly need. And the faculty comments. These are also great. They just don't go through the peer review process, and they might be missing a few things like sample codes or solutions. However, when I went to this collection, I found there were not many exercise sets for modern physics or quantum topics. In fact, I ended up using every single computational activity PICUP has to offer for these topics in my course. So after perusing the PICUP collection, I did what I think 99% of us did in the midst of the COVID-19 pandemic. I went to the Thephet website. Thephet hosts an even broader collection of simulations and activities. So I used the Thephet activities to scaffold up to the coding activities. So in contrast to a PICUP exercise set, Thephet sims are usually inside of an opaque box. You don't get to see the code that's working underneath, but it's a great opportunity to scaffold up to the nitty-gritty computational work because it shows the students what you can accomplish with a computational setup. Still, I didn't have enough to address everything that was in the course objectives. So I spent some time over the summer developing some new activities, one for the PICUP collection and 2 others that are available on my YouTube channel, Let's Code Physics. For the PICUP collection, I submitted an activity on visualizing X-ray diffraction. This was a topic I never really felt like I understood well as an undergraduate because I could never see what was going on based on the crystal structure that was being studied. So I created a Jupyter Notebook activity to complement X-ray diffraction experiments by showing how you can create these diffraction patterns by specifying the lattice structure of the material that you're working with. I was very honored to have that published in the PICUP collection of exercise sets this past year. I also developed an activity to demonstrate relativistic velocity. So what you see here in the second panel is 2 frames of reference created using GlowScript. The first is the red spaceship's reference frame, where they see green spaceship going one way, white spaceship going the other way, each at approximately equal speeds, close to the speed of light. And then at the bottom panel, you see the green spaceship's reference frame. So naturally, it sees red and white going in the same direction, but you notice that it sees them going with approximately the same speed because they're hitting that speed limit of the speed of light. And then I wanted to do a simulation on the Compton scattering effect of scattering photons off of electrons, but I was disappointed that there wasn't anything that really explored the classical analog of scattering an electromagnetic wave off of an electron. So I created 2 simulations. One where you send in an electromagnetic wave and watch the electron oscillate and send out its electromagnetic radiation, which all oscillates at the same frequency. And then I created another simulation to demonstrate photons pelting the electron to demonstrate the collision that changes that wavelength of that photon. This slide outlines the sequencing of these assignments. If you go to the slides in the presentation, you'll find a link to a folder with all of the assignments that I either developed or adopted from the PICUP collection. You might notice that assignments 7 through 11 all have this citation 6. Those are all based on assignment 6, originally written by Andy Runquist. So thank you, Andy, for giving me half of my semester from a single activity. And I graded these assignments based on a specifications rubric. So shout out to Larry Engelhardt. Thank you for providing this rubric and giving an excellent talk about it at PICUP last year, I believe. So the way this specifications grading process worked in my class is that the student would submit their assignment, their Jupyter notebook, and the grader would apply a rubric of yes or no specifications. So you have the specification rubric over here on the right. There are 9 items that each get a yes or a no. There are no partial points because none of these things can really be gradated into partial credit, right? It's either a yes, the assignment accomplishes the specification, or no, it does not accomplish it yet. If all the specifications are met, then the assignment is a pass. The student doesn't have to revisit it. If not all the specifications are met, then it is a not pass yet. Very important to not call this a fail, call it a not pass, because they haven't passed yet. Because what happens then is that the student receives their specifications rubric, they revise their assignment and then resubmit it, and we repeat back at step 2 until we reach the passing score, and then the students are able to move on to the next one. I applied a similar rubric when assessing the students' oral exam. Since this was in the midst of the COVID-19 pandemic, we did not conduct the exams in person. I conducted individual exams with students over Zoom, where I basically conducted almost like a presentation interview. Again, thank you to Larry Engelhardt for the oral exam assessment here. I scheduled these individually with students over Zoom. Each oral exam had a code portion and a problem portion. The students chose an assignment that they had completed to present to me, and I chose a problem from a bank of practice problems for the student to complete for me. And I applied the same rubric to both portions. Again, this is a specifications rubric. The student either gets a check mark or an X on each of them. There's not really much room for partial credit. And I really liked having the exam be 50% the student choosing something and 50% me choosing something, because it still kept up that pressure of the student needs to be able to answer questions that are asked of them, but it also gave the student the opportunity to present what they had learned to me based on what they felt confident. I'll also point out that these oral exams are great, even though they take up a lot of time in your schedule for that week, because you're basically grading them during the oral exam. So it amounts to about the same amount of time you would spend grading the exams anyway. Lastly, I want to talk about the final presentation we conducted in this course. I did not feel that a final exam was an appropriate way to assess what the students had learned in a course that was supposed to introduce them to a plethora of topics, each of which has varying degrees of relevance to their particular future trajectory. And so we had a final presentation that was sort of built up by these pre-class warm-up reading assignments where the students would read one chapter out of the textbook to get them ready for class, and they would read one article's abstract. So in addition to the chapter, I listed several articles and just asked them to read one abstract, not the whole article, just an abstract from that list. And I would ask them, what stood out to you? What's a question that you have? And how is this article related to what you read in the textbook? Interestingly, probably about half the students would read the entire article, not just the abstract. And then the final presentation, I required 3 recent references. I say recent because modern physics should cover modern topics. And the students would take their favorite article from the abstracts they had read, present it to us, look up a couple of related references, and they would basically give a journal club talk. So it was a great way to kind of induct them into the research process while also inducting them into the computational physics practice. So looping back around to computation, I wanted to find out the degree to which the computational assignments helped the students learn the weird concepts of quantum mechanics. We talked at the beginning about the static presentation in Griffiths, and then the dynamic student deductive, inductive learning as they work through a computational activity. And so I asked the students, how did the computational assignments help you learn the weird concepts of quantum mechanics? And overwhelmingly, the students reported that the computational assignments did help them uniquely compared with problem solving or reading the textbook. This student said, I think it was helpful at understanding the weird concepts because you have to think about the various concepts in different ways so that you can put them into a program. So this student saw the computational assignments as a challenge to think about the concepts in different ways in order to actually get them implemented. And it makes you think about it in a different way. It helps you work out some questions that you might not have thought about. This next student said that before the computational assignment, they understood the wave function at a very surface level. So before doing Andy Runquist's assignment, they just sort of had an idea of what the wave function was. But afterwards, they said, I also understood the intricacies involved and why certain energy values mattered. They discovered why we care about the eigenvalues. What makes it an eigenvalue is that it matters to the problem. At first, I couldn't tell you if you just said, hey, look at the book, but with a computational assignment, they were able to actually put it into practice. This next student spent a lot of time talking about how the computer was able to handle the math better than they did, and so you could just run it through to give you less work to do and less time between getting the results. So when working these things out by hand, there's this enormous time delay between the physics and the problem and the physics and the answer, and that sense of what's going on with the physics gets lost in the middle of all that algebra that we saw at the beginning. Student said, I kind of started recognizing relationships rather than plugging something in to a calculator for an hour. Isn't that what we want our students to say about our classes, that they start to recognize relationships? I like this statement. It was more easy to have a coherent thought. Computation here is enabling the student to actually think clearly as opposed to just running around being confused all the time. It made it easier to digest as a student. It was easy to understand the concepts behind it, but to actually work that out on your own would take ages. This student said you could see what happens at each energy level and you could instantly test the energy levels to see what happened. Again, the student values the efficiency for the sake of their learning. They're not just trying to get out of the assignment earlier. They really are valuing the efficiency for the sake of the learning process. It's different from just looking at the integrals involved. See, just looking at, like we did at the beginning of this presentation, and you don't really know what it means. So I want to reiterate my heartfelt gratitude to our supportive community of physics educators. Truly, we have the strength of thousands. I talked about my junior level modern physics in a program that was new to integrating computation. I talked about the significant help that I received from Thephet and the PICUP collection, as well as the new activities I was able to develop. I talked about the specifications-based assessments I incorporated. Thank you again, Larry Engelhardt. And the assessment interviews that I conducted, where computation really seemed to help my students understand the quantum concepts. If you're interested in hearing more about these interviews, we do have 2 other presentations about what the students said, just about their general perceptions, and about how the instructor's views impacted the students' perceptions. Thank you so much for watching. I am looking forward to talking with each of you. Again, if you need anything, please do not hesitate to reach out. I will see you around.